Cool. All right, welcome back to part 5 of this series. I uploaded a tutorial on how to install everything on YouTube. It's about 20 minutes long, but it'll take you about 40 minutes to install everything just because how slow some of it is. Please give that a crack if you're interested in doing some of this stuff and let me know if you run into any problems. I've put a couple of captions over the video where I made slight mistakes in the install. So just follow those if you see them. Cool. So where we left off last week was sort of to the tail end of this resolver stuff. One thing I said last week, I got confused last week as to how this block of code on the right integrates. That's just attached to the bottom of this block. So it's sort of just the rest of the code, and it just deals with the checksum issues. So if there is a checksum fault, it will increment the counter, and above a certain number of counts, it will send CAN errors. And yeah, that's about it. Cool. So onto the chatlets. So these are what the BLCMDs mount into. So we've got a left version and a right version, creatively named Chatlet and Chatret. Cool.
Stands for light.
Now it stands for left and right. Anyway, so yeah, so these are there. So you can see on the back, on the top right, there's the backplane connector, which bolts into the backplane. And then on the bottom here, we've got the power and ground for each lot, as well as the connectors for the resolvers. And these just go directly to the RS485 transceivers, which are on each of those. And then those RS485 transceivers have the TX and RX, the serial, and also the RTS pin, and they go to the connectors to the BLCMDs. One small note is that on here I used a 10K and a 20K pull-up resistors for the RX signal, but those are too big and the time constant is too long, so it doesn't rise fast enough. So I changed them to 1K, 2K, and that fixed that problem. And that's because these resolvers run at 2 megabit, which is actually pretty quick. So yeah, so if you when I was looking on the oscilloscope, you saw a characteristic first order rise and first order fall instead of a nice square wave. The other issue, the original version of this board had the CAN low and CAN high pins backwards on the backplane connector. So that has been fixed on the current version. Yeah, and yeah, and the other thing is obviously the slots labeled pivots are where the pivot BLCMDs go. And if you get that wrong, then they won't be able to talk to the resolvers. And that may have happened before, and they got a call from the US. Yeah. Cool. Couple of other things on the PCB. Hopefully fairly obvious on the left side. We've got the encoder connector here, which is just an RJ45 jack. So we use those twisted pairs for that reason. The motor connector here, which is 3 pins, the SAMTech connector, which plugs into the backplane, into the chatlet. This fan connector, so we've got this heatsink fan, 40 millimeter, that can attach onto there, and those are just automatically controlled with a essentially this fan IC. So the fan IC measures the temperature, and if it gets too hot, it turns on the fan, the thermostat. And then we've got this big DC link capacitor, which deals with on the input. So on the input side, it sort of deals with the suddenly changing current flow in the motor to prevent other things browning out, kind of more or less. Down the bottom here, we've got a PTC fuse, so a positive thermal coefficient fuse. So they are essentially fancy resistors that when they get hot, the resistance increases massively. So if the current exceeds a certain trip value for a certain amount of time, it will then massively increase the resistance so that the current can't go any further. So they're sort of like resettable fuses is what they'll also be called. And then we've got this TBS diode here. So these are both on the 5-volt line. So that TBS diode, if the voltage increases above 5 volts, it will conduct and allow that voltage spike through, and that just creates nice clean power for everything, so we don't end up killing chips.
That sounds like another diode that I know.
Schottky diode, a Zener diode.
Yes.
Yeah, so TVS diodes and Zener diodes are almost identical. Zener diodes have a slower response time.
Okay.
So a TVS diode, a transient voltage suppression diode, is designed to eat up really, really short-lived spikes on the voltage lines and make sure that things don't accidentally die. Cool. So we're sort of going into the code a bit now. This is how the CAN receive stuff is structured. And essentially there's a whole load of commands. So we go from zero to B here. And in fact, this has been updated since we now go up to C. And each of those commands has a behavior. So there's all stop, and we've sort of designed this to be not backwards compatible, but like a similar structure to the CMD command code. So the first one is all stop. So that literally just turns off all the control loops. Twitch forward and twitch backwards, they spin the motor forward and backwards at a certain speed. And then number 3 here, drive at speed. So you pass in, you send the 3 command and a 16-bit hex number, a signed hex, and it will drive at that speed either forwards or backwards. Drive to position does the same thing, but to a position for a position-controlled motor. And then drive at current will drive the current control loop at a set current. Typically, that is a very small current because it'll accelerate really, really quickly if you give it a big current. There's also this drive open loop, which I don't think does anything at the moment. Yeah, so drive open loop is something that someone can potentially try and implement later, where it if it loses all encoder signals, it can still drive, but it's a bit difficult to do that, and it would be very bad. It would be very inefficient. Home rotor is the rotor homing that we talked about. I'm pretty sure in this case it actually just resets the PIC, because when the PIC turns on, the first thing it does is home the rotor. Resolver 0 flag, so in case 8, that next time the resolver is polled, instead of asking its position, it will send the 0 command to the resolver. It's done that way because the resolver commands take a while to run. So yeah, so it'll 0 the resolver. So when you reassemble that gearbox, the resolver isn't necessarily aligned with straight, so you've got to reset that to be 0. And then these last few, so there's get configuration and set configuration. These are mostly unimplemented at the moment, but these allow you to get and set different variables that control the motor. So for instance, things like the number of electrical cycles per mechanical cycle on the motor, things like your PI constants in the PI loops, and that sort of thing. So there's a lot of it's not implemented. There is a list that we would like to implement, but it wasn't a high priority, so it didn't really get done. Yep. Yes, correct. Yeah, so the get and set config are volatile. So they will, if you reset the PIC in any way, it will lose that configuration. So just keep that in mind. The idea being that if you wanted to do it whenever the rover initializes the drive, it would start up and then send all of those commands and check that they're set correctly, and then would start drive. That's how. B here is master reset. So that will reset the PIC. It literally just calls the assembly instruction to reset the PIC. And the last one there is the resolver reset. So there's a different command for the resolver. There's a 0 command and the reset command. And the reset essentially does a power cycle on the resolver. So if you've got weird resolver issues, sometimes that can fix it. Yes, I think they're the same. Although home rotor, we'll have to have a look at the code. I think home rotor may actually work differently, but yeah, the effect is the same because when the pick restarts, it homes the rotor. There's also a bit of stuff here. There's so these are all commands that we would send from the Jetson to the BLCMDs. There's also a column here for the other way around. So any telemetry or information that the BLCMDs are sending. The main one to know about is this $4.0. So that's the errors warning and info message type. And depending on the first byte of that will tell you whether it's an error warning or an info, and the second byte will tell you which error it is or warning. We use a lot of enums for that in the code here. There's also telemetry packets where we get to in a second, and then these 9 and A, these are responses to the get and set configuration. So when you send a get configuration, it will respond with the configuration data, and when you set configuration, it will respond with like a 1 and the data you sent. And yeah, just to be clear, these $signs here are stand-ins for the ID of the BLCMD. So the front left drive is 0, and like the front right pivot, front right pivot I think is 8 or 7. Oh, sorry, front left drive is 1. Yeah, and I start at 1.
Oh, so 1, 2.
Yeah, it's like 1, 2, 3, 4, 5, 6, 7, 8. Yeah, drive and pivots. Yeah. Cool. So this is essentially the main stuff that's in the core control.c file. And what it does is in response to whenever there's a command, for example, this control.allstop. So we would send, on the slide before, we would send command 0 and it would execute control allstop. And that control allstop function is this code here. So what it does is it goes into the X2C model and it sets all of the outputs for the commanded current and velocity to 0. And it also disables all of the control loops. So yeah, so it's fairly self-explanatory. There's this K and out. Essentially, each block has 2 numbers. There's K, which is like the number that's stored inside the block, and there's out, which is the number that's like on the out arrow of that block. I'm not actually you realistically you only need to set one of them. I'm not sure which one does what and how it works. So we just set both of them to 0 to be safe. You could trial and error and figure it out if you want. This is part of the fun of X2C, where the documentation isn't fantastic for some of these things. And the way we do this is sort of not the way you're meant to do it. There's a bunch of state control things that are available in the more premium version of X2C, but we didn't want to pay for it, so we do this instead. So you can see all these enables. So these 3 red tinged blocks. Oh, that one's not red tinged, but those 2 and this one with the red arrows, they're the commanded current, speed, and position. And these switches are they're the toggles between whether it gets commanded directly from this constant block or from the loop above. Okay. So now one thing that's a bit weird maybe is that we don't set the position to be 0. It's probably fine because we immediately disable the control loop. But if you set the position to be 0 and you're not at the 0 position, then the motor might twitch a little bit in that instant. It's not great, I guess. It's just like, I don't know. We might have commented out that code before even testing it because we figured, oh, that's a bit of a weird thing that might happen. For a different example, this control drive to position. So if the first thing it does is check this constant has resolver, and if it doesn't have a resolver, then it will instead run allstop and return because it's not a pivot join. And has resolver gets set in this constants.h file that we have for each motor. And depending on which ID you put in, it will use if depths to define different constants, whether it's a pivot, and like which way forward and backward velocity is and stuff like that. Anyway, so you can see here we set the velocity switch to 1, which means that the current velocity switch to 1, which means that the current commands come from the velocity controller. We set the velocity position switch to 1, which means that the velocity commands come from the position controller. We set the commanded position to be the value that is from the CAN frame, and we enable all of the controllers. Pretty self-explanatory, hopefully. Onto heartbeat. So this occurs in 2 areas on the code. So actually 3 sort of. So in this update inputs function, which is, remember, that's the function that we call to pass updated values for the rotor position and the current into the X2C model. So in that we increment this CAN cycle count incrementer, and in the X2C main loop, if that CAN cycle count is greater than 24414, which is 1 second, then it sends an all stop command and resets that counter and turns the LED. I think that turns the LED off, but anyway. So what that essentially means is if you don't receive a CAN command within 1 second, it will disable any control, anything that the motor is trying to do. So for instance, if the rover was driving forwards towards a cliff and you lost communications, instead of it just not sending a command and then continuing to drive, after 1 second of not receiving command, it stops driving. So that's the reason that's there. This check CAN function in here, essentially all it does, well, the check CAN function is what passes, what like unpacks the CAN messages and all that. But in here, we also have this reset for the CAN count. So whenever it gets a CAN message, it resets the counter, so that if you do receive a CAN message in 1 second, which you should, because it runs at 50 hertz, I think, something like that, then it doesn't stop, basically. That makes sense?
As in, like, the Jetson is sending.
Correct. Or maybe 20 hertz. Yeah, it's sending it significantly faster than once. All right. So telemetry is a bit weird how we've structured it, but it works. Feel free to, again, if you're working on this, you can change this stuff if you like. Oops. So as an example, this telemetry send packet 1, so that there's 4 different packets which we've defined. And packet 1 contains the velocity and the quadrature current measurement. So you can see it gets the velocity using this telemetry get velocity function, which is defined here. Sorry, I've got the zoom blocks all over my screen. Yeah, so it gets the velocity, and it does that by here. It just gets it just goes into the X2C model and pulls out the velocity that's been averaged. Remember in the X2C model, to go back, here this velocity gets like averaged and low pass filtered. So we just take like the output there. It's just sort of arbitrary, but it's an indication of the voltage of the velocity. Sorry. Then it gets the Q current, and it does that again by just reaching into the X2C model to pull out the Q value. Packs it up into this data structure so it bit shifts the velocity to get the upper 8 bits, and then it ANDs it with FF to get the lower 8 bits. Same thing with the current. And then it calls CAN send frame with that data and the number of bytes. And I think the 1 is like the priority or something. And then if we go back to, wow. Sorry. Yeah, you can see here, this is the program flow, right? So there's like the main loop that runs, and then that gets interrupted by the X2C interrupts. And after we update the outputs, we have this telemetry check and send telemetry function. Okay, that was the entire purpose of that. It's a loop. So many slides. So this gets called 24,000 times a second, and essentially it's just this. There's a counter that gets incremented once per loop, and if it divides this number, it sends it. Is that right? 100 hertz? Seems wrong. Anyway, so you can define using that get and set telemetry. Sorry, get and set that like variable CAN method. You can set the speeds that these run at, and I think that works. Yeah. So you can, if you want to get velocities faster, you can say I want you to send it at 10 hertz instead, and it will update the speed so that telemetry packet 1 speed is now 2 instead of being 3, and it'll send it faster. Anyway, if you have a deeper dive into the code, that'll make a bit more sense.
Why is it not typical for what?
It's good enough, I think. I think they're different counters.
Okay.
Yeah, no, good question. Cool. So here's the errors and stuff. So this is enums, which are actually quite a nice thing in C. So you can see here there's this error level enum, and that is either error, warning, or info. So 0 is an error. The way enums work is if you index error level, sorry, if you have a write error, as in like here, it will instantiate that as a 1. So here we write error, and so sorry, as a 0 because the 0th one. Warning will be a 1, info will be a 2. Does that make sense? So all it is essentially in your code, it maps numbers to words so that your code is easier to understand. So here are all the types of errors that we thought might be helpful. No steps. So no steps is if the encoder doesn't give you any steps within a certain period, like any pulses. Magnetic encoder error is for the Pac-Man board, so it's not relevant here / anymore. Resolver error is if the resolver is like disconnected. Resolver failed checksum is if it fails enough checksums. So it's essentially more than 1. Unexpected position command, I think, is an error if a wheel gets commanded to drive and to a position instead of a pivot. However, I don't think that is implemented. So yeah, a lot of these aren't implemented, just as a heads up. So if you're interested in implementing them, feel free. Yeah, correct. Exactly right. Yeah. So in that if has resolver here, it would be sending an error in that. So yeah, it's not hard to implement all of these. It's just sort of tedious and requires a bit of rigor. Gate driver faults. So if there's ever a fault that gets triggered in the gate driver, that will trigger that. That's a very common one if you've got like the motor unplugged or something horrendous going wrong with the motor. Or yeah, there's a lot of things that can trigger that, but if it's sort of if something's shorting out or something like that, it can cause problems like that. Gate driver SPI failed. I've never seen this, but if the gate driver if the communication from the PIC to the gate driver fails to like configure it when on boot, it will give this error. And because if the PIC fails to program, it will not be in the right mode and it just won't work. Sorry, if the gate driver fails to program. MA302 is also the magnetic encoder, so don't worry about that. Rotor home failure. We wrote this in. I don't know if it's possible to detect this. I'm pretty sure it's unimplemented, but if you think of a way, definitely do. Resolver 0 failure is if you send it the 0 command and it doesn't 0. That's also not implemented. And then these two are probably the most important. So the stall triggered. Stall triggered is we have, I haven't got a screenshot, but there's some stuff in the code that measures the current over a set interval. Actually, it measures, what does it measure? Yeah, it measures the commanded current. And if the commanded current, essentially if the wheel is stalled, right, so the wheel is unable to move, the velocity loop will wind up because it's trying to get it to drive, and it'll increase the current to essentially the maximum current it can, right? Mm-hmm. So what we do is we check if the current is above that maximum value for some number of loops corresponding to like half a second or something, then it will trigger this error and it will stop the motor driving. So essentially just is a protection on the motor to make sure it doesn't burn out. This is implemented after we burned out many motors. And back when we were using those really small pivot motors, which we've since ditched because they were not powerful enough in the slightest.
So it stalls for some time.
Correct. So it will send this error. It essentially latch off. So it will, while that error is triggered, it cannot drive, and it will constantly send that error on the canvas. You have to reset it. Yep, yeah. So you have to send that reset command, and it will completely reboot the pick and start over. At the moment it is. In theory, you could make it automated, but you have to be careful because if the motor's stalling and you automatically reset it, then it's just going to cook anyway. Yeah, which also has happened. Yeah. So, is there a situation where the wheel can stall, but it could recover? Kind of. So, like, obviously, there's a bit of arbitrariness in how you set the threshold for this. It's pretty unlikely that if the wheel stalled for the duration that it is currently set to, that it would be able to recover without first repositioning the rover. So you could definitely recover, but you would want to move the rover into a different position so that wheel. It's mainly we haven't stalled. I don't think we've stalled the motor since we've switched the motors, so it's sort of less important nowadays. But yeah, something. And lastly is the overspeed flag. Now this is a very fun one, and this comes from an issue that we touched on a couple of weeks back, where if your rotor home doesn't work correctly, then there's a chance that your positive velocity direction and your positive current direction will be not the same direction. If that makes sense. So if the control loops are trying to increase the velocity, it will apply a torque in the opposite direction. And then the velocity loops will go, I'm spinning negative at the wrong speed, like negative speed instead of positive speed. I'm going to increase my current so that I start driving forward. And it will actually ramp the speed up fully negative and wreak havoc. So what this overspeed flag does is essentially catch that case. And the way it does it is that if the commanded speed is at the saturated limit for a certain amount of time, it will cut the motor. So it's basically a similar sort of thing, but on the velocity loop instead of the current. Yeah, so you can have a look into how that works as well, the overspeed flag. In fact, we touch on it in the slides. Sorry?
I assume it's somehow being.
Actually, no. If it's wired, if the encoder is wired backwards, it should still work exactly the same because both your rotor position and your velocity will be switched. Right? The reason it happens is if the homing doesn't work properly, such that it homes more than 90 degrees away from where it should. So it thinks it's at home, but it's actually more than 90 degrees out. So when it tries to apply positive Q, it's actually applying positive Q, which spins it the wrong way. Yeah, it's a bit hard to wrap your head around, but you'll understand it when you start to play with it. Cool. So gate driver faults, as past me is helpfully written, these typically only occur when you're pushing the things really, really hard. So like really high speed, fast accelerations, that sort of thing. And like sudden transitions in like applied voltage and stuff like that. And this is part of the reason why we have some of those ramp filters on the rate limiters in the blocks. Originally, we automatically cleared this fault. However, there was a time where we were killing gate drivers somewhat randomly. And we believe it was because we were clearing this fault immediately when it occurred. So the gate driver was reinitializing immediately on the next loop, and it was still in an unsafe state. So it was like blowing up basically. So that doesn't happen anymore. Instead, we just set a flag and you reset the flag by commanding it when you can. Yeah, so if you correct, yeah, and it's QFM as well. So yeah, if the gate driver dies, it's a real pain in the ass because it's a very, very fine pitch chip, and yeah, getting it to solder correctly by hand is quite annoying. But it is possible. If it blows up at comp, you're better off having an entire spare BLCMD. But yes, take some just in case. But yeah, because yeah, resoldering those in the field, like you can only really do it with a hot plate. Yeah. Yeah. So this handle fault, it used to clear the fault, but now I think it just does nothing. In fact, yeah. Anyway. Stall fault, here you go. So yeah, if the commanded current is more than the max current minus 1,000, so more than the maximum, so essentially like the max current is the maximum possible current we can apply, and the max current minus 1,000 is some threshold below that, right? So if the commanded current is in that threshold, it increments this counter, and when that counter exceeds half a second worth of counts, it sets the stall flag. Essentially, it's only if you're pushing the command current super hard for a long time, it'll trigger the fault. If it's less than that value, then it will actually decrement that count. Okay. Like just hard coded numbers. Well, because then if you have divisions, it has to calculate that every time. Well, maybe not, but like you got to be careful, right? Sometimes it's just easier to hard code a number in there to make sure that the compiler is actually putting the number in there instead of calculating it at runtime, because that would slow things down a lot if it's having to do a floating point division or something.
Sure.
Overspeed fault. So yeah, so essentially it only yeah, so if as I was saying before, yeah, so all this does is get the value of the velocity command, right? And if it's negative, then it just multiplies it by -1 to get the absolute value. And if that velocity is exceeding the maximum commandable velocity by this extra amount, which is completely arbitrary, but we just pick that, it increments this counter. Otherwise, it decrements the counter. So basically how that works is there is a maximum speed that we can command the motor to spin at, right? But there is also a maximum speed that the motor can spin at, which is bigger, right? So if we command, if something goes wrong and the BLCMD is trying to command the motor to spin, sorry, something goes wrong and the motor is spinning faster than we can command it to spin, something's gone wrong. And it's also gone wrong by more than by 4,800 speed units by that. So clearly something has gone horribly wrong and it increments that speed counter. Now we've got these counters so that it just like doesn't because sometimes it will just trip randomly, right? Like you get a bit of noise fluctuation, and it'll happen. And then yeah, so when the counter's above 256, it'll hit the flag. Yeah, go.
Yeah, so with this overspeed fault, I was just wondering, I remember at some of the earlier field tests when you were first testing the BLCMDs, you had that issue where it would just like the pivots would just keep rotating.
Yeah.
So is this fault meant to stop that issue?
exactly right. Yeah, that's exactly for that reason. So if essentially the pivots, something went wrong with the homing, and the reason the homing didn't work was because the grub screws were loose. And when that happened, the pivot essentially spun the wrong so it would try to move the pivot to a certain position, and instead the pivot spun the wrong direction at the fastest speed the motor could spin at, and then it wound up the cabling inside and caused a bunch of damage and was really, really bad. So yeah, this is how that fixes that. So it sets this flag, this overspeed flag, and when at the start of the control loop stuff code, if the overspeed flag is set, it just runs it commands all stop instead of whatever is command. Yeah, maybe we fixed it. Oh, we never. Maybe I think it's underflow. No. Okay, yeah, you might be right. Anyway, whatever. Resolve a fault we went over. So if it's failing a checksum or getting no response, you can reset the resolver itself by clicking C. And I think this is automated. Yeah, okay. This is the config over CAN stuff I was talking about. I'm not going to go into a ton of detail, but essentially you can set the configuration by passing this like variable index, which references which variable you wanting to change, and also passing it the data that you want to set that variable to. So you got things like set the current P constant, set the current I constant. A lot of this is not implemented or doesn't work properly. So again, something for someone to do if they are so pleased. But yeah, essentially it has and the way that the PI blocks store the value for the P and I constants, KP and KI, is quite strange. It uses fractionals and it uses these shift right by or something, and then the data. I don't understand how it works. So yeah, feel free to dive into that. It's kind of nightmarish.
Right now we just
Yes. Yeah. So it's a bit annoying at the moment. Ideally, we would be able to set these in code so that when we change the ID of the thing, like in this constants H file, right? One of them is the ID of the port, so 1 through 8, right? And depending on what that ID is, it sets a bunch of different parameters. And at the moment, we can't change the PI constants in code because we don't understand how this works.
Yeah.
So once you do understand how this works, then you can do that. And then you'll never have, because at the moment we have to go into the XTC model, change all the numbers when we switch from pivots to drive because the constants are different. So once someone figures that out, that'll fix that issue. Yes. Mhm. Yeah. So the question was if you send it a command and then update these constants like while the commands are running, will it cause issues? It shouldn't, and that's just because everything runs really quickly, and because these updates happen actually between the control loop calls. I think, kind of more or less. Yeah, you might want to be a little bit careful. You might want to like set it to all stop, change it, undo it, that sort of thing. But probably fine. Yeah, talked about that. Can I be bothered going to this right now? Yeah, so one thing, so the current capacity is quite important. So it's essentially this is sort of around the current capacity of the inverter, right? How much current can it output? And because we have current control, we can exactly like control the torque at the motor, which is pretty helpful. So for example, if we were to pick a motor such as the R80s, which we use on the pivots, there's this graph here, and you can see that the continuous torque region is at any speed is more or less up to 1.3 Newton meters, and getting 1.3 Newton meters takes 15 amps of current. So that's to do with the KT constant, right? So it's a value that's in Newton meters per amp. There's this short-term operation, which is for a couple of seconds, where it can do up to 4 Newton meters and draws 46 amps, which is a lot. And worth noting that these are DC or RMS currents, not it gets a bit confusing because like technically we're applying an AC voltage to this thing, right? So, but the DC current, the Q current is essentially a DC current. You can think of it that way. So yeah, essentially we designed, well, when I say we, Christos targeted 50 amps DC for the inverter. So we can actually supply, it can, if you wanted it to, it could supply this 4 Newton meters torque, which is enormous on the output of the motor. Like 4 Newton meters would completely destroy the gearbox, I'm pretty sure, if you applied it. And the output was locked. But yeah, in retrospect, it's probably pretty overkill targeting 50 amps DC because we actually operate the pivot motors at this limited this continuous torque limit just to be safe. In theory, we could actually run it up to 4 because it's only a short-term operation, but really it's fast enough for what we need. We don't need it to accelerate that much quicker than it already does.
Time to
This is from the data sheet.
okay.
Yeah. So the only note is that it's for 48 volts, but all that will do, right, is that the voltage. Remember, the voltage is proportional to the velocity. So this RPM curve, it essentially just pulls down the maximum speed because we run it at like 36 volts. So the maximum speed drops from like 5,250 RPM to probably like 4,000, 3,500 ish or something.
No.
No, rerun this at 36 volts. But that's the maximum it can run. Now, the thing to remember is like this applied voltage is not the voltage of the battery that we're powering it, right? It's the Q voltage that gets applied to the motor, right? So when we say we're applying 30 volts, we're essentially applying and if our battery was 36 volts, which it roughly is, 30 volts is what, 80% of 36. So no, it's not. Okay, so say the battery is 30 volts and we're applying 20 volts to the motor by PWMing the motor down to 2/3, right? So we would be operating at the 20 volt line, which is probably, I don't know, like 2,000 RPM or something. And obviously, as you apply more torque to the motor, the speed it can run at gets slower because if you think about, vehicles IR plus the back EMF, so as you apply torque, that current increases, so the IR term gets bigger, which means that the back EMF term can't grow as big before V gets saturated. Make sense? So it all comes back. There's so many different ways you can think about that vehicle's IR plus back EMF equation, depending on what's fixed and what's not fixed. But yeah, if you get one thing out of this whole series of videos, it's that equation because it is really helpful. And my slides is completely. 1 second. Cool. Bit of stuff on the ripple current. Probably best if maybe Christos goes back over this in another video as well. But sort of just like how you design the size of that DC link capacitor. And because there's actually a bit going on. I was planning to do this for like all the different components on the board, but I didn't have time. But it's interesting to look that so we're targeting 30 amps, and we Yeah. So you can see, yeah. So you can see here this capacitor current divided by the phase current. So there's a lot of different currents going on here because we're going from DC to AC. So there's the current flowing in and out of the capacitor, and there's the current flowing through the motor. And this modulation index it tells you what proportion of your input voltage is on the output. But you can see here that if we have a phase angle between and then each of these lines is the phase angle, right, between the current and the voltage. If you have a phase angle of 1, which is the worst case, the capacitor current is worst case around 60% of the voltage of the coil current. Does that make sense? No? Cool. So if we basically this graph here is a function of the modulation index, which is the duty cycle, right? On the inverter. Yeah. Yeah. So like it's essentially it's the ratio of the output voltage to the input voltage, right? So if we have 20 volts on the input and 20 volts on the output, that's a modulation. Then if we have a phase angle between the current and the voltage of 0 degrees, that means cos of phi is 1. So this is like power factor, right? Anyway, point is the peak. So each of these lines is different power factors, but the peak value is about 0.6, roughly 0.6, 0.7. And this is the capacitor current divided by the phase current. So essentially what it's saying is that if you want 50 amps through your coil, you need 30 amps capacitor current, like capacity, right? The current needs to be able to oscillate with 30 amps of current. So we targeted 50 amps. Obviously, in retrospect, probably a bit overkill, but here we are. So 30 amps. It can. Apparently. Well, we've never tested. Anyway, so now the other factor is that depending on the frequency, you have to derate that capacitance even further. So this table is from the data sheet of the capacitor. So we run at 24 kilohertz, and so it's pretty good. Somewhere between 95% and 1, which is not bad. Obviously, the lower the frequency, the worse things are for a capacitor because it becomes more and more DC like. Anyway, there's some links there, resource on how you sort of size all of these. It explains it much better than I am now. Yeah, essentially. So it's a thermal limit, and it's to do with the internal resistance of the capacitance, and potentially some other things, but I think it's mainly, yeah, I'm pretty sure it's mainly the thermal limit, and it's just that the capacitors can deal with a certain amount of ripple current, and that's what we're sizing here. So you need to find capacitors that are suited for that. So that might end up meaning that you have a very large capacitor that has a large ripple current capacity compared to, like for example, a tantalum capacitor probably wouldn't work because you wouldn't be able to find one big enough with a large enough voltage that can handle this sort of frequency. But tantalums are good for high frequency, not a means. But anyway, that's just sort of a very poorly explained thing to explain that there is a lot going on in that sort of design. Yeah. So what I'm going to do, I mean, it's nearly 4. Does anyone have any questions on anything to do with this? Sorry, whatever the maximum we can do is 30 watts. Yeah, I think fully charged battery. Oh yeah, 4.2 times 8. Yeah, fair enough. Yeah, but the maximum we can do is battery.
Say like some spike.
Uh, it would eat the spike and nothing much would happen. It wouldn't be an infinite current. It would be a large current. So yeah, like the capacitor, the alternate way to think that is there's a spike in voltage and the capacitor is a low impedance path for high frequency signals. So that spike would pass through the capacitor to ground.
Yeah.
But also we have TBS diodes, so they would eat those instead.
Okay.
Yeah.
Yeah.
So my plan for this session next week is if there's any like this is all of the content essentially. So I'm probably gonna like go into using like the MP lab, just sort of explore the code with everyone there. So if you could try and get it installed before then, that'd be really good. But also, yeah, if there's any like fundamental questions that you've still got, you just don't understand something, then let me know then, because or even beforehand, so I can prep a bit, so that we can go through that together. And then I think later next, potentially Tuesday next week, I'm just organizing with Christos. We'll have an in-person like practical workshop on how to use X2C with the rover there, and probably getting into like some of the tuning of the PID and stuff like that. Yeah, that sort of thing. Hooking up the X2C probe and all of that. Oh, it's just the UART line, the little blue cable. Yeah, so that gives us the yes. Yeah. Yeah.
Wow.
Cool. Any final questions? All right.
Would you tell
I'll stop the recording.